everyone, my name is Alexander Lee. This is my Physics 2212 Lab 3, which is about circuits. So here are some of the things we're going to be going over today. So quick introductory, and then theory, models, experiment, discussion, and conclusion. So a quick introduction about this lab. So the purpose of this lab is to apply energy and current conservation principles to predict circuit behavior, measure current and voltage using multimeter, and examine resistors and capacitors. So the system is going to be the circuit, the surrounding is going to be everything else. Conditions are going to be, so we have two 1.5 volt batteries, two resistors in series, a 47 ohm and a 100 ohm resistor, 2 ammeters, and then here are our results. So charging and discharging time vary depending on if we're using 10 or 20 ohms, and then the node and loop rules are proven. So here are some theories. So the node rule, which is current flowing into a node, must equal to the current flowing out of it, result of charge conservation. And the loop rule is the sum of all electric potential differences around a loop is zero. This is the result of energy conservation. And then we got Ohm's law, which is current through a conductor between 2 points is directly proportional to the voltage across the points. So charge conservation and energy conservation in series circuits. So we predict that the currents in I1 and I2 would be measured by the 2 ammeters. We notice that the current is the same everywhere, but what happens if we reverse the connection to one of the ammeters? So charge conservation and energy conservation in series circuits. So what happens if we convert one of the ammeters to a voltmeter by charging the mode on the multimeter? So the ammeter reads 0 amperage because the voltmeter has a very high resistance. The voltmeter reads 3 volts since there's no other voltage drop in the circuit. And then the picture down here is just us conducting our experiment. So here's our experiment. So our current we got to be 0.06 amps, and then the electric potential. So these are our electric potential across each point. So from A to B, it's 3 volt. From B to C, it's 0 volts. From C to D, it's negative 0.96 volts. D to E, 0. E to F, negative 2. F to G is 0. G to H is 0. And then H to A is also 0. So the actual is 0.01 volts, the expected 0 volts, and the resistance of each circuit element. So here we got the 47 resistor, and then we got the 100 resistor, and then we got the resistance of the wire. So here are our potential versus position graph. And then here's the energy conservation. So the ammeter has a low resistance, so the electron will flow through the ammeter. Instead, this will lower the overall resistance of the circuit, and the total resistance is now 47 ohms instead of 147 ohms. So this is our second experiment, which is the charging of the light bulb. And here, after connecting the battery to one of the bulbs, the brightness gets dimmer after some time. When you connect the capacitor to the bulb directly, then the bulb gets brighter at first, then it gets dimmer. And here are our times for each of the bulbs. And so I want to go over some possible sources of error. So there could be human error from stopping the stopwatch and the capacitor from discharging at the same time. And there could be imprecisions of the ammeter readings and calculations rounding. So what if you charge the capacitor without a resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So with no resistor, the ideal model would predict the capacitor to charge instantly. Not happen in real life. Batteries have internal resistance. So use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery. Why is the measured time different from the predicted time? So when measured with an ammeter, the capacitor charges more slowly than predicted due to internal resistance in the circuit and non-ideal components. So in conclusion, our data is somewhat similar to our predicted data. And then in this lab, we're going about DC and RC circuits and predicted and examined their behaviors. All right, thank you.